So good afternoon, everybody. Thank you very much for being here. This is one more edition of our QRC seminar. It's great to see so many faces. Thanks for the experimentalists for coming. I know that many people have traveled to the March meeting this week, so it's not the same amount of people as usual. And thanks for being here, those that stayed. So today I have the pleasure of introducing you to Dr. Daniel Stilt-Franza. Daniel, he did PhD with Michael Wolf in Munich. He did postdocs in Copenhagen with Matthias Christander. So both Michael Wolf and Matthias Christander, these are heavyweights of quantum information theory and the like. Daniel is in a meteoric career. After his first postdoc, he went straight to getting some sort of tenure track in Lyon, in École Normale Supérieure de Lyon and INRIA, where he's an assistant professor, right? He's in the same group as people like Omar Fozzi, and it's part of an initiative, well-funded initiative, and he's having lots of nice results on learning and characterizing quantum devices, also quantum algorithms. And he started a group in Lyon where he has some nice positions, and the group is growing. And he gave a talk in QIP in Belgium, and that's where we said, okay, yeah, it would be great to have you here in Abu Dhabi, which he kindly accepted the invitation. He will be here for the rest of the week. He took the time to stay with us for the week and talk to everybody. So it's great that he's giving his talk today. We'll have the week for having more discussions. So Daniel, thank you very much for being here. It's great to have you here. I hope this is the beginning of many visits. Please proceed. Thank you.
Yeah. Thanks a lot, Brandon, for this very kind introduction. I probably even blushed a bit and all those kind words. So yeah, I'm here to talk about some work on the limitations imposed by noise on near-term algorithms for optimization. This is based on essentially two papers, but also a third I'll mention in the end. One with Paul Garcia-Patron, and the other one with Giacomo De Palma, Candice Jose, and Milad Mardian. At the end, I'll also mention some follow-up work I did with Isaac in Berlin. So please also interrupt me at any point if you have questions. I'm always happy to discuss. Oh, now it's stopped working. Strange. Well, probably we have to switch to the preview. Where is it?
Click on the presentation.
Okay, so let me describe the problem we care about. So we'll be given some Hamiltonian. We'll have n qubits, and we want to maybe when we care about a certain problem, and the solution to that problem is encoded in the ground state of this Hamiltonian. So in this talk, I'll mostly focus on classical problems. So you can think for simplicity throughout this talk that you want to find the ground state of some Ising Hamiltonian, okay? And you want to maybe not necessarily get the ground state on the nose. You're happy with, let's say, a state of low enough energy, and you want to solve this problem on a NISQ device, so noise intermediate scale quantum devices. So in particular, this means that we can either implement very shallow circuits so that we can still not feel the pain the noise causes very strongly, or very noisy circuits at the expense of having a non-trivial density of errors when we're solving this problem. And the guiding question is, how likely is it that we can actually use such devices to solve these problems and actually obtain a quantum advantage compared to classical approaches? So there are a few facts to keep in mind. First, that we're not completely lost when it comes to solving these problems with classical computers. Of course, there are thousands of people who devoted their careers to that. We have tons of heuristics, but also very good, rigorous algorithms. So, it's not like we're competing against a weak adversary when we're trying to find good solutions to these problems on a classical quantum device. And again, I should stress that for most applications, it doesn't really matter whether you found the exact ground state or something close to that. So we'll be interested in knowing like whether the energy that we output with some efficient classical algorithm or some heuristic algorithm is potentially better or worse than the one you obtain with a noisy quantum computer. So what kind of algorithm will we talk about and analyze? One example is the QAOA, Quantum Approximate Optimization Algorithm. This was proposed by Farhi and co-authors in 2014. And these algorithms have drawn a lot of attention. As evidence to that, I plotted the number of citations per year of the original paper. You can see it has exponential growth. The R square is almost it's 0.97. The growth rate is 2.26. The last 2021 is a bit off, but I hope that 22 will pick up the pace and go up here again. But you know how exponential growth works. So in a few years, everybody will be working on this, right? That's the only conclusion here. So of course, this is just a teaser, but just to point out that these things have drawn a lot of attention. And how do they look like? Well, essentially it works like this. You write down a parametrized family of Hamiltonians, of unitaries, and you intersperse unitaries which are proportional to the Hamiltonian that encodes your energy with those which are just like sum of poly X. And you sort of try to pick these parameters in a way such that the energy that you get at the end is minimal. So that's the whole idea of this algorithm. You sort of do some sort of optimization loop to obtain the best values for these parameters at the end here. And we can actually show rigorously that as you let the number of layers go to infinity, you find the ground state on the nodes. So when you let these guys go to infinity, you'll measure the ground state here at the end, because this is some sort of discretized adiabatic algorithm. So that's why as you let L go to infinity, you find the solution. But one hopes that already for a few layers, this produces good outcomes or good strings.
So
And
is it evolution parameters?
yes, so yeah. Oh yeah, sorry. By this I mean like sorry.
And H0 here is the Ising-Hamiltonian.
No, HI is the Ising-Hamiltonian. H0 is just sum of poly outside. So like intersperse like sum of poly xi with the Ising. Other questions?
The ground state that I measure is it ground state of classical system?
Yes.
Okay.
Yeah, so you want to find the ground state of a classical system of an Ising model.
Yeah.
So you're interested in this string that comes out at the end.
The final string gives us the ground state or close to the state which is close to ground.
Exactly. So the hope is that you find very good parameters in some way. You run this thing on your quantum device and you measure some output string. And the hope is that the energy you'll get at the end, which is just like this, the string will be very close to the ground state. And we want to ask ourselves, like, can we find good solutions to Ising problems, which in some sense are like computationally universal for combinatorial optimization through such schemes.
What's the purpose here of using HI and the initializing Hamiltonian? Can we replace it by some simple Hamiltonian?
Yeah. So the question is why I do this Hadamard's?
No. The white block. Yeah.
This block and this block?
No, the HI block.
Oh, the HI block.
Can we replace the HI, the initializing Hamiltonian? Let's say like our initializing Hamiltonian would be super complicated, fully connected. Can we replace here by, let's say, one de-Ising or two de-Ising?
Well, in general, you do need these two things. So the idea here, if you think of continuous time, right? That we first do a layer of Hadamard's that will give us a bunch of pluses.
Yeah.
So this will be the ground state of this thing over here. And if you think of the continuous time version, you want to like do some sort of adiabatic evolution from the ground state of this to the ground state of this, which is the thing you care about. So it is in general important that you also have the Hamiltonian that encodes your problem.
Okay, in this sense, it can be proven that the final state will be ground state of the isotope.
If you let L go to infinity.
Yeah.
So because then you could think of this as like you pick these parameters like you pick these parameters here very large at the beginning and let them go to 0, and these one very small and let them go to 1, and then you have some sort of adiabatic evolution that will go from the ground state of this. Does that make sense?
Yes.
Yes.
Yeah.
Very, very even stupid question. Say a classical system doesn't have a ground state.
What do you mean?
A classical system has the lowest energy.
I mean, yeah,
Energy, right? What is the ground state?
it's just the bit strength.
Is
Right.
what? Spins.
Yeah.
So the spin. So you want the configuration of all the icing spins.
Exactly. Yes.
So
And
in the basis in which H is there.
exactly. Yes. Yes. And this is a very hard problem in general, because you can encode NP complete problems this way. So that's why in some sense it's universal. If you can solve this problem, you can solve any, let's say, traveling salesman or things like that. And that's also why people care about this, because these are problems with practical applications. Okay.
One question, like you're saying that there's a proof that in L to infinity, does that use the adiabatic theorem? Or is it kind of
I mean, if I had to prove it now, this is what I would do it. There might be other more elegant or simple proofs.
Because I recently learned about the mathematical intricacies of actually having the adiabatic theorem. So
Yeah.
do they also apply here?
So to have an adiabatic theorem, you have to you need some estimate on the spectral gap of the Hamiltonian throughout the thing, but you can show that it's like unique. And then if you let the time go to infinity, at one point you'll be slower than the gap, so you're fine. There's more, the uniqueness might be a problem. Other questions? No, okay, then I'll continue. But in the near term, you won't be implementing this thing because there's noise. And we don't expect to have access to a lot of error correction in the near term. So again, either we implement a very shallow version of this where we don't see a lot of noise, or we do a longer thing and there will be some noise present. And the question is, how will this affect the performance of these devices? So instead of doing a unitary, it will be interspersed by some sort of noisy channel that will cause some problems. Now, in the first step in analyzing this, I'll consider the simplest possible local noise model, which is the polarizing noise on each qubit. So I must say I really enjoyed this experience so far. So here, if you want to hear about more complicated noise models, invite me again. I'll come gladly. But in principle, we'll just think about this very simple noise model as the first step. And we want to look at the expectation value of the energy of the outputs. Okay, and then I'll move on later to a more complicated scenario where we actually care about concentration inequality. So I'll explain what that means in a second. So let's see what happens, right? As the number of layers increases, the more noise we apply. So in this system, in this noise model, with some probability p, nothing happens to one qubit, and with probability 1 minus p, it gets replaced by something completely random, just a maximum mixed state, right? So as we do more and more layers of this circuit, at one point we'll have replaced all of our qubits by the maximally mixed state. And if you measure this in the computational basis, you just get a uniformly random sample. There's no reason to use a quantum computer for that. You can easily just flip some coins and you get the same result, right? So in some sense, you'd also expect that you wouldn't get anything interesting if you're already close enough to that scenario. But what is close enough in the sense of losing advantage for these problems, and when does that happen? How can we estimate that? And in particular, we want to be able to compare what the knowledge quantum computer is doing to these classical, very effective algorithms we have today. Not necessarily rigorous, also heuristic algorithms. And you might also expect that somehow, if you're only allowed to do very shallow circuits, maybe this isn't enough to beat good classical algorithms that can run for long, right? So we want to be able to say, well, maybe because it's shallow, we can't do good enough, we can't find good enough solutions. Maybe because of the noise, we can't find good enough solutions. And what is important is that I want to decouple this question from the question of how difficult it is to simulate this noisy quantum device. So simulating noise and simulating noisy quantum systems is very hard, right? So it doesn't mean, but it doesn't mean that they're doing something useful. So these are two different questions, right? It might be the case that you cannot simulate some noisy quantum device, but it doesn't mean that whatever this noisy device is doing it's interesting because it's hard to simulate it, right? So, so we want to decouple these two notions. And again, as we want to find a minimal energy, we'll say that we lost quantum advantage whenever the expected energy that this quantum algorithm outputs with respect to this Ising Hamiltonian is larger than that of what we obtain with our favorite heuristic or whatever algorithm. This is our definition of what it means to be useless at this point. And what we concluded in this paper is that if your local noise rate is P, let's say the probability that a gate fails is 1%, already at depths which are like 5 to 10, you're sampling from distributions that have very low energies. So and so just to show you an example, so we found a technique to bound the performance of noisy quantum devices solving optimization problems, which gives you bounds on how well a quantum device can perform for a given optimization task, given noise levels. And then you can compare it to, for instance, your favorite classical algorithm. Okay, so here I plotted what our technique predicts for solving, to finding ground states of the SK model, which is like a family of random Ising models. And here this bar means if an algorithm hits this bar, it means it found the exact minimum. Okay, if this bar is what we know we can reach with efficient classical algorithms. So for quantum to be better than efficient classical algorithms, we would need to go from here to here, right? This is the region where we don't necessarily know how to find.
Y-axis?
Y-axis is the ratio between the energy you get and the true minimum. So 1 means that you're at the ground state energy.
No, can find the minimum best.
So the energy of the ground state is known.
Okay, so
yeah. So in this case, and you know that there are classical algorithms that are known to reach this ratio. Okay, so if the quantum computer needs to do something useful, it has to be in this range.
But fix this ratio is like what is it how it scales with the number of qubits?
I mean, so the ratio is constant in the number of qubits. Does not depend on the number of qubits.
No. I mean the Wily curve, the blue curve, around like this curve, this line around
this
around
one.
0.6. Yeah, this one.
Yes. So the ratio between the true ground state and let's say the true ground state is n, as like minus n, say. And there is then an efficient classical algorithm that always achieves like minus 62, say, n, 0.62.
For any number of qubits.
For any number of qubits. Yes.
So the only figure of merit is how close you get the ground state, no, not how long you
you take to get there?
No, this is efficient. This is efficient.
No, but in general.
I mean, these are, okay, this is an important point I forgot to mention. As these are classical problems, right? We know that the best string will always be just classical, right? Ups and downs. So in principle, you could go through 2 to the n of them and find the best one. So we're only interested in algorithms that do better than 2 to the n.
So and how do you define do better?
How do you define, sorry?
Do better.
Do better. Well, if you find a lower energy, right?
With less time than just going through all of them.
Exactly. And what I'm claiming is that there is this algorithm that if you have like n qubits runs in, let's say, n squared or something. I think this one you can make it run in n squared, but let's say n cubed for just to be on the safe side, that will reach this part. So you know, there is not really if you want like an exponentially better thing, then you need to somehow be able to produce strings which are in this region.
Yeah. So you bound the amount of optimization loops and function calls for the QAOA to the same one as the classically efficient method?
No. So what we do is the following. So this is the next point. Imagine now that you are implementing QAOA, but you're not implementing QAOA on a noiseless device. You're implementing it on a noisy device. So in this case here, I think it's for 6 layers of QAOA. And then, but you know, we have noise. And what our technique tells us is that this is the best you could do with this amount of noise. Yeah. No error mitigation. We'll get to that in a second. I mean, not in a second. This will take like 30 minutes. So if I forget about it, let me.
Sorry, the Ising model that you're using to get the statistic in this plot also have some transverse field or just
no. So in this case, no transverse field.
Okay, then Gilman Williamson should have like.
It's not approximation ratio. It's energy of that model, right?
No. So I mean, okay, very technical subtlety. Gomez and Williamson is for max cut, right? So these are Ising models where all the interactions have the same sign, and the ratio, the proof of the ratio uses that fact. If you don't, in this SK model, the signs are picked at random.
Okay.
And then as you have these differences, the approximation ratio also changes. So that's fine. Okay. Very, very good. You're paying very close attention. Right. Yeah. So what our techniques tells us is that if you're running these noisy quantum algorithms on noisy devices, already because of the noise present in there, this is the best you could reach. So because of the noise alone, you wouldn't be able to even get close to the to what you can do with your laptop, right? And what is nice is that Google also implemented this algorithm 2 years ago, and we see that with our bounds, we would have already been able to tell them that they're not going to do anything good, right? So as the noise level increases, we get close. So we see that noise really constrains our ability to reach good strings for these problems.
Sorry, but here even the noiseless quantum case is worse than a classical efficient algorithm.
That is correct. So if we go back, like as I said, you have to do L going to infinity for you to get good solutions. In this case, they picked L equals 6. If my memory doesn't fail me, it is known that if you pick L like 22, you will be able to go here, like in this region in the noiseless case. But already with L equals 6, you see that the performance is decaying rapidly, right? So if with L equals 6, they're not able to observe anything good, it means that trying to go for 21 is is pointless, right? And I should also mention that somehow this is what you get if you just sample it, right? So they're still doing better than random sampling, right? But not.
So Daniel, just one question, sorry. So the orange points are the experiments by Google,
yeah.
And the dark points, this know your limits. This is
the bound we get in this work. Like this is how well we predict, even if they find the best possible circuit to solve this problem
for a fixed number of layers.
Yeah,
right.
Yeah.
And fixed noise.
Yeah, and
right.
Fixed noise. This is the best they could have achieved.
Okay.
So in some sense, you might also indicate this as like, hey, like considering this is the best they could have achieved, then QAOA is already getting closer.
Right.
Maybe.
Okay.
Yeah.
I didn't see where you could get because we were pointing with the laser point, and I cannot see this.
Sorry.
You have here that you have
the 6 qubits are down.
Yeah.
You say that actually 20 qubits no noise is in between the. No, it's not qubit, it's layers. The layers. In between the pink and the blue. No? So you can you are in the gap for 22 layers. But for 6 layers, noisy, you are always down. Yeah.
So in between 0.6 and 1.
Yes.
Yeah.
So if you could run the noiseless thingy with 22 layers, you would have gone above what you can do with your.
Then your bound depends also on the number of layers, or is this?
Yes, it does. It does. As you increase the number of layers, the more noise you pump into the system. So worse.
It will always go down.
It will always go down as you increase. Yeah.
Can we interpret this y-axis as a probability, success probability?
We'll get to success probability later as well. So even though you asked the question first, I'll get to your question first and then his later. So we'll shift later to success probability and then okay.
So it's interesting. We could spend the entire seminar on this slide essentially, right?
Yeah, it's already been half. So maybe I'll go to the next one. I guess we already had some nice discussions. Let me just think on what to focus. I won't. Wanted to give you some idea of how we plot how we bound the performance of these devices, and the idea is to essentially compare noisy quantum devices to finite temperature states somehow. So the idea is that if you think of this computation, right? It starts at 0, which you can think of as some sort of ground state, right? And as you add more and more noise, you will converge to an infinite temperature state. Somehow in the noiseless computation, you will try to go to this other ground state of this problem you care about, but the noise will drive you to the infinite temperature. And then by working on some entropic inequalities, we can compare how well this noisy quantum device will perform with another Gibbs state. And we show that the more noise you add, this corresponds to somehow increasing the temperature of what you're doing. So that's more or less on a very high level how the technique works. Exactly, now going back to his question, I only talked about the expectation value, but you could think of an algorithm that does whose performance is terrible in expectation, but in practice would be wonderful, which is like with probability 1/2, you output the best string, and with probability 1/2, you output the worst string. And in expectation, this will be terrible because these will cancel out. But if I only care about getting one good low energy string, I'm very happy with such an algorithm, right? Because it's somehow, if I measure a few times, I'll see the optimal string. So maybe this definition of looking at just the expectation value is too loose for these problems, and we should actually look at the probability of observing even one low energy string. And we'll say that we lost quantum advantage if this becomes exponentially small. So again, EQ is the energy you get by measuring your noisy quantum device, and EC is the energy you get when you run your favorite classical algorithm. And if this is exponentially small, then, well, we have to use your quantum computer exponentially many times to see something that beats your laptop.
So, Daniel, this is the probability of one string sample from a quantum experiment having less energy than the solution that a classical solver would give you.
Yes.
Okay.
Yeah. And
also, I think you can mention anything about how much time it takes to train your quantum.
Doesn't matter. I only care about like the like also this EC might be the output of a heuristic.
So it's given the best possibly trained quantum QAUA.
Yes.
How it compares with the best.
Yes. And error mitigation as well, but well, maybe I'll skip some of the technicalities and just mention that once again, if you measure a system in the maximally mixed state, which is the state we get if we apply an infinite amount of noise, then the probability that so in expectation the energy you observe is 0, and what's happening is actually that the probability that you deviate by some epsilon times n will be like e to the minus epsilon squared times n. Okay, so for this state over here, the state where you have a lot of noise, the probability of seeing a large deviation from the expectation value is exponentially small. And again, the question is how much noise do we need to pump into the system so that the outputs also of the noisy quantum device behave in a similar fashion, right? That, you know, the probability of deviating too much from the expectation value is small, exponentially small. And going back to the comment before, we actually want small already like small deviations will move you away from what can be done from in the classical realm, because we have some pretty good classical algorithms. Okay, so what is going on? We'll start with this all plus state, we'll apply some noise. This will just give us the uniform distribution. So the probability of something good happening is exponentially small. However, at the other end, we'll also have the plus state in algorithms like QAOA. If you measure it in the computational basis, it will also be uniformly distributed. So at the beginning and at the end, in the noisy case, what we'll measure will only have an exponentially small probability of deviating and getting us something interesting. And the question is, can something interesting happen in between, right? In terms of also the output probabilities. And it turns out that we use a thing called sandwiched Renyi divergences, which are given by this ugly expression over here, to compare somehow the concentration properties of measuring in this noisy quantum state versus just what are the concentration properties when measured in this like infinite noise limit. And yeah, they are used in quantum, these sandwich Renyi entropies are used in quantum information theory, for instance, to understand concentration properties of states. And by using the sandwich Renyi divergences, we actually show that all you need to understand to be able to say something about the concentration properties of outcomes of these noisy devices is just this Renyi divergence between your output state and the maximally mixed state. And you should think of these divergences as some sort of distance measure. It's not really a distance measure, but it's close enough that also allows you to infer something about the distribution of the outcomes and how well they're concentrated.
So Daniel, sorry, one question. So when you talk about concentration, you're thinking about a random ensemble, right? Like something concentrates over what? Who's random here? Sorry.
I'm being too fast now.
No, sure.
So the question is as follows. So concentration inequalities, they quantify how likely you are to deviate from the mean. So in this case, our random ensemble is just what we get when we measure this quantum state in the computational basis. This is our distribution. And then we evaluate the energy with respect to this Ising model. And we have the question is, how likely is this energy to deviate significantly from the mean?
But the Hamiltonian, the target Hamiltonian is fixed, and the input state is fixed as the ground state of the uniform.
Yeah, the only thing, the randomness comes from the
measurements. Okay.
Other questions as I raised a lot?
Why do we need different alphas?
Oh, why do we need different alphas? So some alphas are nicer than others. So like I particularly like alpha equals 2. So I just wrote the bound in all generality, but for instance, as you see, if you can control this thing with alpha going to infinity, this term will go to 1, so it will become stronger, but this thing then also becomes more difficult to control. And as I do in the next slide, I actually like to take alpha equals to 2, because that's the easiest one to control.
Alpha equals to 2 is a mutual inclusion.
No, alpha equals to 2 is like some variation of the purity of the state. Yeah. So what we can show, for instance, is that the alpha will decay exponentially in the depth of the circuit. So you're somehow, if you take this metric, you get closer and closer to this maximally mixed state in this metric at an exponential rate. And this rate only depends on the local noise rate. So it doesn't matter how many qubits you have, the rate will be the same. And we show that it only has to contract by a constant fraction. So Q is, in this case, for instance, if you consider an n-qubit depolarizing channel, then the Q will be 1 minus the polarizing probability, for instance. So for instance, if you have a local depolarizing rate of, say, the error rate is 0.01, then this Q will be 0.99. So putting these things together, we show that at constant depth, so like a depth that only is like 1 over constant noise rate, the probability of even observing one output string that is interesting in the sense that it beats a classical algorithm is exponentially small. So, okay.
So it's better than a previous bound, because previously we saw S2 to the power of minus 2, and now just minus 1.
They are different statements, right? The other one was about the expected value. Now I can control the whole probability.
Yes, so if we control the whole probability, then we obtain a better result.
Exactly.
So it's a good idea to observe separate outcomes, not just a mean value.
Yes, exactly. Okay, so we see that if we pump a bit of noise into the system, then well, the probability of getting something interesting will be exponentially small. But we haven't talked about this end, right? Because it could be that you're just running very shallow circuits, and let's say that 4 or 5, and you could ask the question, well, maybe these are so shallow that the noise will not affect the quality of the devices. But then again, the question is, can you actually reach good solutions if you only have a few operations, right? And it turns out that these concentration properties also allow you to find instances where the answer is no. Okay, so let me quickly explain what is the connection between concentration and no-go results for like preparing certain states. So imagine that you want to prepare your a JZ state. So superpositions of zeros and all ones. If you look at the local observable, which is just sum over Zi over the different qubits, then the expectation value of this observable is 0 because you either observe all zeros or all ones, right? These have values n and minus n, 50-50. So the expectation value is 0. But as I was saying, Leandro, concentration is about how close you're likely to be to the mean. In the case of the JZ state, you're going to be as far away as possible from the mean, right? Because the mean will be over here, and you'll always be either at this extreme or this extreme. So states like the JZ state have no concentration. So on the other hand, like concentrated distributions look a bit like this, you know, like most, the fat is around the mean. And we somehow see that if we have the property that a family of circuit concentrates, then it cannot be preparing states like the JZ, right? Does that make sense? Cool. So, and what we do here is to show that outcomes of shallow circuits actually concentrate. So we get bounds on the tail of the distributions, how much fat there is as you move away from the mean.
Sorry, but it depends on the observable, right?
Local observables, yes. So okay, we there is this part I skipped, which is something I called the Lipschitz constant. So this thing here, you should think of it as a measure of how local the observable is. So if you have very non-local observables, then this bound is not saying anything. But so there, indeed, if you have very non-local observables, then it could be that they're not concentrated. But for local observables and shallow circuits, you have sort of tail.
And it doesn't matter what's the local observable is.
No.
So you can choose A, or like you choose all X's, right?
Yes. Oh no. Sorry. Maybe yeah. By local observable, I mean like something that is, for instance, an average over few body observables. So that's what I mean. So not product, but like for instance, average over a few body observables. Something like the energy of a local thing.
But for example, in the case of the exam sets that you're interested in, you should be able to prepare them with a single depth circuit.
Excellent point. We're getting very good questions, which leads me to, I mean, I'll just skip this part to get to his point, which is here. So the very good observation is that we are only interested in product states, but QAOA cannot work like that because as Krish observed in this work, you have a symmetry in these circuits. Because both the Ising Hamiltonian and the other Hamiltonian you're implementing, they commute with X tensor n, which means that you cannot do what you're suggesting. You cannot just like implement these algorithms. They have this structure and the symmetry, and one can show then using this that there are certain Hamiltonians whose all the somehow non-trivial strings look like JZ states. Okay, so that's not our construction. That's the construction from this paper, where they show that there are like Ising models where all the good strings are JZ like, and we show that shallow circuits. We find simplified proofs that if you have, for instance, a constant depth circuit, then you have concentration.
So it's a constant depth QAOA.
No, so okay, two things. So like any circuit any shallow circuit has concentration, and what we need the QoA for is to say that like if it's gonna find a good solution, it's gonna have this symmetry, and therefore the optimal solutions it needs to find are highly entangled. So concentration holds for any circuit, but we use the symmetry of QoA to say that these algorithms, even though we are interested only on a product string, because of the symmetry, if they find the solution, it will be highly entangled. Does that make sense?
So we are saying that if the classical Hamiltonian will be degenerate, right? For instance, then we have this is a hardest case, right?
No. All I'm saying is the following. So imagine even if you just I don't know, like had the his point is more, as we are only interested in a classical string, right?
Yeah,
the solution is a classical string. Then there is a depth 1 circuit that prepares it. You just flip the right thing.
Yeah, okay.
So how am I saying that shallow circuits cannot find solutions to this problem? Nonsense, right? Well, I'm restricting to this particular class of quantum circuits, which happen to have this symmetry. So because of this, they cannot just prepare any quantum state. Throughout the evolution, you have to respect this symmetry. So I mean, if you want, this some sort of like symmetry perfection, which implies that you cannot really find ground states very fast. Okay, so in particular, we get a very loose, not loose, but not a particularly great, from a numerical perspective, lower bound on how many layers you have to apply this QoA thing in order to observe good solutions, okay? And what I want to point out is the fact that you have a log n here, right? So if you, I mean, if you do some computations, the number of like n has to be huge for this to be very limiting. So it's not too practically relevant, this lower bound, I would say. But it shows that if you want to, with these QoA like circuits, if you want to reach good solutions, then the number of layers has to scale with system size for these instances. But we also showed that at constant depth, the noise will kill you. So you need to go to system size dependent depths to see interesting solutions. Constant size, the noise will kill you. So there's no quantum advantage for these instances at constant noise levels. And as far as I know, it's like the first proof of that. So
but to prove that, you're using the usual QoA circuits, right?
Yes.
That, for instance, but what if we just let's say we have kind of a bunch of CNOTs and the 1 qubit gates parameterized, right? So can we achieve something further?
Okay. So I mean, I sort of plugged my own work a bit too much here and forgot to include other interesting results in the literature. There's also work by Farhi, where they show that if you have any sort of local algorithm that somehow looks at a neighborhood of each vertex and then decides to do what it should, each qubit decides what it should do, then similar bounds hold. But again, we cannot, I mean, there are quantum circuits of depth 1 that do the trick, right? So it's not like they don't exist. The question is about finding them. So I don't know if I really answered the question.
Yeah, well, I don't know. I think about the quantum circuit as, let's say, the ansatz, right? Variational ansatz.
Okay.
You can put in your variational ansatz what you want, actually. You can put CNOTs and one qubit case, right? And then try to have this ansatz, try to minimize.
Yeah, sure. So I guess the in general, I mean, I cannot promise you that for any ansatz it won't work. I don't think we have a risk. I mean, because of the noise, yes, but for these lower bounds, Yeah, I mean, again, by the reason that, for instance, if your ansatz is just a layer of parameterized, Pauli X that you turn on or not, then the solution will always be contained.
That's okay. I can understand.
Yeah.
But I mean, like say you have some entangling gates like CNOTs and for instance, I have one layer of CNOTs, which entangles each pair of qubits. And then the second layer would be single qubit gates, which angles I can rotate, right? And then again and again and again and again. So this is would be kind of Hamiltonian dependent ansatz, Hamiltonian independent ansatz. So for this kind of ansatz, can I find the better, let's say, the better probability?
Because of the performance decay, because of the noise will be the same. The noise doesn't care about your ansatz. For this bit, I think that if you want to do it for a general ansatz, you won't be able to prove anything. But whether it will perform better in practice or not, I don't know, to be honest.
So this relies on this symmetry, right?
Yeah,
Side of the.
So, but there are other results that don't rely on the symmetry, but rather on the fact that it's like the algorithm is in some sense loop. That because roughly the idea is that, for instance, if you want to prepare something like a JZ state, you need to make all the qubits talk to each other, and these other arguments just use that. So that if you didn't make all the qubits talk to each other, then you cannot get something.
Sorry, I have a question. So logarithm of n, stupid question, seems to be very optimistic bound. So even for large, if n grows, then the depth grows not so rapidly, and so probably that's good. So what's the problem?
What's the problem? Well, the problem is, I mean, I completely agree with you that this isn't a very terrible bound. The problem is that this is not saying that it will work at log n. This is only saying it will definitely not work if you go below that.
Okay.
Because I mean, in general, it's very difficult to get lower bounds because you have to predict, like, no matter what you do, it won't work, right? And this is telling you that if you don't go to log n, it will not work. It might if you're very optimistic, it might be the case that if you go slightly above log n, it works. I don't think we have a lot of evidence for that. But the point is that if the noise is constant, right, and you log n grows, so at one point these two curves will. Yeah. Other questions?
The lower bound also depends on the margin.
No, this lower bound is completely like this even holds for the noiseless case. Even in a noiseless case, this lower bound holds. So even if you had no noise, this holds.
So Daniel, we should try to go for 15 minutes.
Okay, sure. Then maybe I can briefly touch on error mitigation. So that but I'll be around for the rest of the week, so I'll be happy to talk about it in more detail. So what is error mitigation? So error mitigation is about the following idea. I was mostly considering the case where you run a circuit, a noisy circuit, you sample from it, and you either get some expectation values or samples from it. In error mitigation, you run a bunch of circuits, maybe not necessarily the original circuit you were interested in, but some like variations. You run a bunch of copies, you measure them, you do some classical post-processing to sort of try to filter out the noise, and then get like cleaner expectation values or samples. So are we all on the same page when it comes to what error mitigation is? So like some sort of, you run the circuit a bunch of times and try to filter out the signal from the noise, roughly speaking. And there are 2 points that I think are important when you're talking about error mitigation. First is that in these problems, we are often not interested in knowing what the ground state energy is. Sometimes that's also the case, but most often we are interested in knowing, like an assignment, a string that achieves that. Okay. And as far as I'm aware, most error mitigation techniques only try to filter out noiseless expectation values. So if you want to actually get a clean string, I don't think there are many things known in this direction. Okay, but still, let's still consider that. So maybe I won't talk about this, but what we show in another recent work is that also applying error mitigation won't change the conclusion, in the sense that if you have a local noise rate of P and you have L layers of noise the circuit has L layers, if you want to extract noiseless expectation values from the noisy states, the number of samples you need will grow exponentially with the number of layers. And what I find maybe more interesting is that for certain circuits, it's even worse. So for certain circuits, the number of samples you need will actually grow exponentially with system size. So if you go at depths like log square n, not very deep, for certain circuits, if you want to extract even one noiseless expectation value to precision 1/2, which isn't too big, right? You need exponentially many samples.
Sorry, but again, for the entire optimization, you don't need expectations.
You need bit strings, yes. So, I mean, that's another fundamental reason why you might say that current error mitigation techniques are not well suited for this problem. I completely agree with that. But like, even if you only care about expectation values, then already like an exponential amount of.
But can you change the error mitigation technique to like try to optimize the minimum of your error? Let's say if you have at the end, you have a bunch of distance, right?
Mm-hmm.
And then you are trying to kind of align your gates such that your distribution of the, let's say, bit strings would move to the minimum of your energy landscape.
Mm-hmm. But what I'm saying is that, let's suppose that if you understand error mitigation as like you're given access to a family of noisy quantum circuits, and you want to extract like an expectation value of a noiseless circuit, if that is your understanding of error mitigation, then the number of samples you need from those noisy quantum circuits will explode.
Daniel, I have a very simple scenario in mind. So if you prepare a circuit and you kind of hope that the output of that circuit is going to be close to the bit string that you want to find, then you can measure sigma z locally on each of the n qubits, right? And from the expectation value of each of those, you will have like the kind of like the reduced state on each single qubit, and then you will be able to make an educated guess whether it's in 0 or 1 locally, right? And then this could serve you to transform local expectation values into a bit string, right?
Yes. And I mean, you're just describing what our proof strategy is somehow. So the idea is that if you had access to these local expectation values, you could sort of identify the output, right? And
you do error mitigation in those observables.
Exactly, and then then you do some information theory to say that there should be no algorithm that is able to. There's so much noise that there is no algorithm that should be able to distinguish outputs of these circuits. So let's say there's no algorithm that should be able to distinguish the string you get if you input all zeros or if you input all ones. Say. Does that make sense?
Yeah. Okay.
But this result I mentioned has many caveats. So one of the caveats is that it doesn't hold for all circuits. So for certain circuits, the number of samples you need to do error mitigation does not scale with the number of qubits, right? Because here I'm saying that it scales not only with the depth, but also with the number of qubits, which is significantly worse, right? But you could think of one circuit where this doesn't happen, which is the circuit where you don't do anything. So let's say you do L layers of identity, then and you want to just recover one local observable. As there is no interaction, then the amount of samples you need to do this recovery will only depend on the local noise rate. However, we construct many sufficiently entangling or deep circuits such that all the qubits are somehow correlated and the noise really kills you. And then you get the system size dependence. So one, I'll skip the technical part. Okay, so one of the problems with this other result where we show this exponential scaling is that it says nothing about, let's say, QAOA circuits. So it could be the case that for QAOA circuits, or other circuits you might care about, the number of the samples doesn't depend on the number of qubits, just like the number of layers. Or it could be that they behave like these very pathological examples we constructed, where it's exponential scaling in both, like, let's say, the volume of the circuit. So like number of qubits and layers. So that's I think still an open question. As I mentioned before, I only considered the polarizing noise model. And what I didn't tell you is that for some noise models that are very natural, say pure amplitude damping, this whole framework breaks down. Like it's worthless. So the question is then, does would the noise model also change the qualitatively the conclusions or not? And I think another interesting question is, well, we see that from these results that it's unlikely that we'll get very good solutions with no error correction. The question is how much error correction then we might need to potentially have quantum speedups for these classes of problems. And with that, thanks for the attention. It was really nice to give this.
Thank you very much, Daniel. Congratulations on the great results, and thanks for the talk. There's been questions. Do we have a couple more maybe to finish the session?
Oh no, so that's a very good question. So essentially, I mean, we didn't find an error mitigation technique in the literature for which our results didn't apply, but maybe there is some. I mean, there's so many now out there that it's difficult to say, but from all the ones I'm aware of, it applies.
So I have another, like, maybe tech detail. So the conclusion is or one of the main conclusions is, if the local noise strength or the depolarizing channel is P, then after a number of layers of order 1/P, then you're toasted essentially, right? And then, so these results, so to prove that, so it's in terms of the number of layers, right? But each layer, in fact, if I think of compilations in terms of 2-qubit gates, so if we're talking about, you may have like a Ising Hamiltonian that connects qubits that are very far away, and to implement each of the 2-qubit interaction terms in the Hamiltonian, you would need like itself for a single layer, like non-local circuits, right? Which inflate the noise even more. So this 1/P refers to the circuit depth or to the number of layers?
to the actual like physical depth.
Depth.
So we have drawn back to this picture where we all started. Because you see that the number of qubits is growing, right? But the number of layers is constant. So it's like 6. And the quality gets worse, right? Why? Because although the number of QoA layers is fixed, as this model has a lot of connectivity,
right,
when you actually compile it into the machine, which as the title makes clear is planar, if you want to make qubits far away talk, you have to do some swaps and so on. So even though like when you write down the unitary, the number of layers is fixed, when you actually transport it, compile it to the device, the depth increases and therefore more.
I see. Great. And sorry, since taking advantage of this question, so the bound by Clich and others, so log n, it also refers to number of layers, right? Yeah. Not circuit depth, right? Yeah. Okay, great. Thanks.
And
because you're underestimating the amount of noise.
No, it's because like the bound is somehow like the best imaginable circuit you could. Even the best imaginable circuit you could implement with this amount of noise could have this performance, and this is like the one specific circuit they're implementing.
But
so
imaginable means upper bound. It's not proved that this bound is achievable.
Yes.
Any other urgent question? Daniel is going to be around for the next days. We can continue discussing. Right. If not, then let's thank the speaker again for a nice talk.